Algebra by Michael Artin. Section 8. Products of groups. Let G and G' be two groups. The product set G cross G' can be made into a group by component-wise multiplication. That is, we define multiplication of pairs by the rule 8.1. The pair A, A' and B, B' is mapped to the pair AB, A'B'. For A, B a member of G and A', B' a member of G'. The pair 1, 1 is an identity, and A, A' inverse is equal to A inverse, A' inverse. The associative law in G cross G' follows from the fact that it holds in G and in G'. The group thus obtained is called the product of G and G' and is denoted by G cross G'. Its order is the product of the orders of G and G'. The product group is related to the two factors G and G' in a simple way, which we can sum up in terms of some homomorphisms, defined by I of x equal x, 1. I prime of x prime is equal to 1, x prime. P of x, x prime is equal to x. P prime of x, x prime is equal to x prime. The maps I and I prime are injective and may be used to identify G and G' with the subgroups G cross 1, 1 cross G' of G cross G'. The maps P and P' are surjective. The kernel of P is equal to 1 cross G', and the kernel of P' is equal to G cross 1. These maps are called the projections. Being kernels, G cross 1 and 1 cross G' are normal subgroups of G cross G'. 8.3. Proposition. The mapping property of products. Let H be any group. The homomorphisms phi mapping H to G cross G' are in bijective correspondence with pairs phi, phi' of homomorphisms, phi mapping H to G, phi' mapping H to G'. The kernel of phi is the intersection, the kernel of phi intersected with the kernel of phi'. Proof. Given a pair phi, phi' of homomorphisms, we define the corresponding homomorphism, phi mapping H to G cross G' by the rule phi of H is equal to phi of H, phi' of H. This is easily seen to be a homomorphism. Conversely, given phi, we obtain phi and phi' by composition with the projections, as phi equal p phi, p' equal p' phi. Obviously, phi of H is equal to 1, 1, if and only if phi of H is equal to 1 and phi' of H is equal to 1, which shows that the kernel of phi is equal to the kernel of phi intersected with the kernel of phi'. It is clearly desirable to compose a given group G as a product, meaning to find two groups H and H' such that G is isomorphic to the product H cross H'. For the groups H, H' will be smaller and therefore simpler, and the relation between H cross H' and its factors is easily understood. Unfortunately, it is quite rare that a given group is a product, but it does happen occasionally. For example, it is rather surprising that a cyclic group of order 6 can be decomposed. A cyclic group C6 of order 6 is isomorphic to the product C2 cross C3 of cyclic groups of orders 2 and 3. This can be shown using the mapping property just discussed. Say that C6 is equal to 1, x squared, x to the 5th power. C2 is equal to 1, y. C3 is equal to 1, z squared. The rule phi mapping C6 to C2 cross C3 defined by phi of x to the I equal y to the I, z to the I is a homomorphism, and its kernel is the set of elements x to the I power such that y to the I power is equal to 1 and z to the I power is equal to 1. Now, y to the I power equal 1 if and only if I is divisible by 2, while z to the I power equals 1 if and only if I is divisible by 3. There is no integer between 1 and 5 which is divisible by both 2 and 3. Therefore, the kernel of phi is equal to the identity set, and phi is injective. Since both groups have order 6, phi is bijective and hence is an isomorphism. The same argument works for cyclic groups of order Rs, whenever the two integers R and S have no common factor. 8.4. Proposition. Let R and S be integers with no common factor. A cyclic group of order Rs is isomorphic to the product of a cyclic group of order R and a cyclic group of order S. On the other hand, a cyclic group of order 4 is not isomorphic to a product of two cyclic groups of order 2, for it is easily seen that every element of C2 cross C2 has order 1 or 2, whereas a cyclic group of order 4 contains two elements of order 4, and the proposition makes no assertions about a group which is not cyclic. Let A and B be subsets of a group G, then we denote the set of products of elements of A and B by 8.5. AB is equal to the set X a member of G such that X is equal AB for some A a member of A and B a member of B. The next proposition characterizes product groups. 8.6. Proposition. Let H and K be subgroups of G. A. If H intersect K is equal to the identity, the product map P mapping H cross K to G defined by P of H, K equal HK is injective. Its image is the subset HK. B. If either H or K is a normal subgroup of G, then the product sets HK and KH are equal, and HK is a subgroup of G. C. If H and K are normal, H intersect K is equal the identity, and HK equal G, then G is isomorphic to the product group H cross K. Proof. A. Let H1, K1, H2, K2 be elements of H cross K, such that H1K1 is equal to H2K2. Multiplying both sides of this equation, on the left by H1 inverse and on the right by K2 inverse, we find K1, K2 inverse is equal to H1 inverse H2. Since H intersect K is equal to the identity, H1, H2 inverse equal H1 inverse H2 equal the identity. Since H1 equal H2 and K1 equal K2, this shows that P is injective. B. Suppose that H is a normal subgroup of G, and let H be a member of H and K a member of K. Note that KH equal the quantity KHK inverse times K. Since H is normal, KHK inverse is a member of H. Therefore, KH is a member of HK, which shows that KH is a subset of HK. The proof of the other inclusion is similar. The fact that HK is a subgroup now follows easily. For closure under multiplication, note that in a product, the quantity HK times the quantity H prime K prime is equal to H times the quantity KH prime times K prime. The middle term, KH prime, is in KH equal HK. Say KH prime equal H double prime K double prime. Then HK H prime K prime is equal to the quantity H double prime times the quantity K double prime K prime, which is a member of HK. Closure under inverses is similar. The quantity HK inverse is equal to K inverse H inverse, which is a member of KH equal HK. And of course, 1 equals 1 times 1 is a member of HK. Thus HK is a subgroup. The proof is similar in the case that K is normal. C. Assume that both subgroups are normal, and that H intersect K is equal to 1. Consider the product, the quantity HKH inverse times K inverse is equal to H times the quantity KH inverse K inverse. Since K is a normal subgroup, the left side is in K. Since H is normal, the right side is in H. Thus, this product is the intersection H intersect K, i.e., HKH inverse K inverse is equal to 1. Therefore, HK is equal to KH. This being known, the fact that P is a homomorphism follows directly. In the group H cross K, the product rule is quantity H1, K1 times quantity H2, K2 is equal to H1, H2, K1, K2. And this element corresponds to H1, H2, K1, K2 in G. while in G the products H1K1 and H2K2 multiply as H1K1, H2K2. Since H2K1 is equal to K1H2, the products are equal. Part A shows that P is injective, and the assumption that HK is equal to G shows that P is surjective. It is important to note that the product map P mapping H cross K to G will not be a group homomorphism unless the two subgroups commute with each other. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall. It is read by Jim Renholt with programming and illustration by Jim Renholt, 2019. Thank you for listening.